stretched, compressed, or twisted into any shape. And yet the fundamental physics you observe remains exactly the same. Sounds like something out of a science fiction novel, right? This isn't fiction. It's a revolutionary idea at the heart of what we're diving into today. Welcome to the Deep Dive. Mitchell. Today we're embarking on a journey into topological quantum field theory, or TQFT for short. Now, for most of physics, think general relativity, the local geometry of spacetime, this really mind-bending concept. We'll explore how it beautifully bridges the worlds of pure mathematics and theoretical physics and discover its surprising, tangible applications, from exotic states of matter to, well, the future of quantum computing. We're pulling insights from a fantastic source, Topological Invariants, Bridging Physics and Mathematics, which is an excellent job synthesizing quantum field theory, geometry, and modern physics. So you ready? Let's unpack this.
It's truly a fascinating departure. I mean, in traditional physics, the metric tensor, that mathematical object defining distances and angles, is a very active player. It's the stage, upon which everything unfolds. TQFT, however, chooses to kind of ignore that stage. It focuses instead on properties that remain absolutely unchanged, even if you continuously deform spacetime. Think of it like a topologist classifying shapes.
Yeah.
A donut and a coffee cup are the same to them because they both have one hole, right? Regardless of how you stretch or squash them.
Okay, so it's about the holes, not the exact shape.
Exactly. And instead of predicting the probability of, say, a particle scattering off another, TQFT calculates what we call topological invariants. These are numbers or maybe algebraic structures that classify the global shapes of spacetime itself or the global properties of the system. What this ultimately means is that TQFTs aren't describing fast-moving local particles in the usual sense. The Hamiltonian, which is the engine for time evolution in most theories, often becomes trivial, effectively zero. These theories describe the deep, robust, low-energy properties of systems, the universal features that persist even when all the local noisy details are just disregarded.
That's a powerful reframing. For someone used to, say, trapping a planet's orbit, how do we intuitively grasp physics without those local geometric details? Does this mean we lose all sense of motion or interaction, or are we just, looking at it through a different lens?
That's a great question. You're not losing all sense of interaction, but you're looking at a different kind of interaction. It's not about the continuous, smooth motion we see in classical mechanics or even standard quantum field theory. Instead, it's about discrete, global changes. For example, if you braid two quantum objects around each other, the pattern of that braid, its topological class, that's what matters, not the exact wiggly path they took. It's a lens that deliberately blurs out the local noise to reveal the underlying robust structure.
That clarifies it. So if local geometry disappears, it's not about how fast a particle is moving or exactly where it is, but more about the fundamental essence of the space it lives in, a truly unique perspective moving beyond the local stuff.
Precisely. It's a shift in focus to the global, unchanging properties.
So how did physicists and mathematicians even dream up such a radical concept? What's truly captivating about this is that this profound shift wasn't born from one single brilliant mind, right? Instead, it was a remarkable convergence of ideas back in the 1980s, a real intellectual fusion. On the mathematics side, for instance, you have Simon Donaldson making these incredible strides. By studying specific finite energy solutions to gauge theory equations, people often call them instantons, and the abstract spaces that classify them, he uncovered astonishing new polynomial invariants for 4D manifolds, which is completely new math. And almost concurrently, Andreas Floer, inspired by earlier work on supersymmetry, developed a new homology theory for three-manifolds, using similar powerful gauge-theoretic ingredients, these mathematical tools rooted in symmetries.
Right, these mathematical breakthroughs were profound in their own right. But the natural next question then became, could these abstract mathematical constructs somehow be found, in the physical world? Sir Michael Atiyah was the visionary who really connected these seemingly disparate mathematical dots. He conjectured that these newly discovered invariants were actually the observables of a completely new type of quantum field theory, a topological one.
So he saw the physical potential in the pure math.
Exactly. But it was Edward Witten in these seminal papers in 1988 who then provided the concrete physical realizations. He demonstrated how a specially twisted version of a supersymmetric Yang-Mills theory could precisely reproduce Donaldson's invariants. And crucially, he showed how another theory, Chern-Simons theory, could provide a physical framework for the Jones polynomial and other fascinating invariants of knots and links.
Knots and links, like actual knots.
Like actual knots, yes. This wasn't just an analogy, it was the moment the abstract mathematical world found a tangible home in physics. It showed that physics could offer powerful intuition for pure math, and vice versa, a real two-way street.
It sounds like a true intellectual breakthrough, where two distinct fields suddenly just illuminated each other. Okay, so if we accept this idea, how do we actually build a TQFT? What are the blueprints for such a theory?
Well, essentially, TQFTs generally fall into two main categories, and they're defined by how they achieve their independence from the metric. First, we have what are called Schwartz-type TQFTs. Here, the mathematical framework defining the theory, the action functional, is explicitly metric independent right from the start. Its topological invariance is, as we sometimes say, baked in. There are just no terms that depend on distances or angles in its fundamental definition. You could stretch or squeeze the spacetime, and the underlying mass description stays exactly the same.
Okay, so born topological.
Right. Chern-Simons theory, which we'll talk more about, is the prime example of this type. Then we have Witten type, or cohomological TQFTs. Now, these are a bit more subtle. They actually start with a theory that is metric-dependent one that describes local particles and interactions, like a supersymmetric Yang-Mills theory. But then metric independence sort of emerges through this clever procedure known as a topological twist.
A twist. What does that mean exactly?
It involves redefining how the fields of the theory transform under certain symmetries. This clever twist works by realigning how we think about the theory's internal symmetries, with the profound result that the energy-momentum tensor, which usually dictates local dynamics, effectively becomes trivial in a specific mathematical way. This makes all observable quantities completely independent of any local metric changes. And the calculations in these theories often simplify dramatically. They sort of localize onto a finite dimensional space of special solutions, things like those instantons we mentioned.
Okay, so one class is inherently topological by design, while the other is sort of twisted to become topological. Both get to the same place, removing dependence on local geometry, but through different kinds of clever mathematical engineering almost.
That's a good way to put it. Different paths to the same metric-independent summit.
Let's get more concrete now. What are the shining examples of TQFT in action? Where can we really see this mathematical magic at play?
Absolutely. Let's start with a theory that literally helps us understand knots. The three-dimensional Chern-Simons gauge theory is arguably the most celebrated example of a Schwartz-type TQFT. Its action, the formula defining it, is constructed purely from something called a connection field, a mathematical object that tells you how to compare things at different points, but it explicitly omits any mention of distances or angles.
Right, no metric.
No metric. So it's inherently independent of the geometry of the 3D space. Now, for the quantum theory to be well defined, a certain coupling constant, called the level, has to be a precise integer. That's important. Now, here's the truly astonishing part. The key observables in Chern-Simons theory are these things called Wilson loops. Imagine a tiny quantum string tracing out a closed loop in this 3D space, basically like a knot.
Okay.
The vacuum expectation values of these Wilson loops, which are what the theory actually predicts you'd measure, were discovered by Witten back in 1989 to be precisely the knot polynomials that mathematicians had discovered purely combinatorially.
Wait, really? The exact same polynomials?
The exact same ones. For example, for a specific symmetry group, SU2, it computes the famous Joan the polynomial. For other groups, it computes others. It wasn't just an analogy, it was a profound, exact correspondence. It gave the powerful machinery of quantum field theory a direct tool to study pure topology. Even subtle mathematical ambiguities in defining certain knot invariants were clarified by the physical requirements of quantum field theory, like needing something called framing.
That's incredible. A physical theory literally calculating properties of knots, which seem purely mathematical. Wow. Now, if Chern-Simons showed us the elegance of a naturally topological theory, what about the other kind? The Donaldson-Witten theory shows us the power of that topological twist, right, to reveal the deep structure of even higher dimensional spaces.
That's exactly right. This is a 4D Witten-type TQFT. It starts with a standard theory, ends with two supersymmetric Yang-Mills, which does depend on the metric and describes propagating particles. Standard physics initially. But then the topological twist mechanism comes into play. It essentially redefines how certain quantum fields transform, leading to a situation where the energy-momentum tensor, the thing that usually determines local dynamics, becomes exact in a specific mathematical sense, related to a symmetry operator, Q.
Q exact.
And this makes all the theory's observables robustly independent of the local metric. Then the path integral, which is how we calculate probabilities in quantum field theory, undergoes this dramatic simplification. Instead of integrating over an infinite number of possible field configurations, it localizes onto a finite dimensional space of very specific solutions, these anti-self-dual connections, or instantons.
Same instantons Donaldson used.
The very same mathematical objects that Donaldson himself used to define his invariance of four manifolds, the correlation functions, the actual predictions of this twisted physical theory, were found to be mathematically identical to the Donaldson polynomial invariance. It was this extraordinary physical reinterpretation of deep, abstract mathematical concepts. It effectively gave a physical home to Donaldson's work on four manifolds, and it even explained how, for a four-manifold with a 3D boundary, the quantum states living on that boundary precisely corresponded to Floer homology, revealing this really profound connection between all these mathematical structures.
Just amazing. The connections are so deep. So TQFT isn't just about connecting abstract math with theoretical physics then. It's also unlocking incredibly concrete, even futuristic applications right here in our physical world. Let's explore some of those areas where TQFT is making a real tangible impact.
Yeah, absolutely. One of the most exciting areas is definitely in condensed matter physics, particularly with the emergence of what we call topological order. You see, in many quantum systems at extremely low energies, the frantic local dynamics often just disappear, they average out. Instead, the physics becomes governed by the robust global properties of the ground state's entanglement structure.
Entanglement structure.
Exactly. And this is precisely the domain that a TQFT is perfectly suited to describe. The fractional quantum Hall effect, or FQHE, is the classic example here. Imagine a 2D electron gas trapped in a powerful magnetic field at temperatures near absolute zero. Under these conditions, the Hall conductance, a measure of how current flows sideways, isn't just quantized, like in the integer effect, it's quantized in fractional multiples of the fundamental constant, like 13 or 25. That's something impossible for ordinary individual electrons.
Right. Fractions are weird for electrons.
Very weird. And it turns out the effective low-energy theory for the FQHE is a 2 plus 1 dimensional abelian Chern-Simons theory, where that level constant k we mentioned directly corresponds to that fractional filling factor. And here's where it truly gets astonishing. The excitations above this FQHE ground state aren't your typical electrons or holes. They are these exotic quasi-particles called anyons. These things can carry fractional electric charges, like E3, but even more profoundly, they exhibit what's called braiding statistics. In 2D, unlike 3D, if you exchange two of these anyons by moving them around each other, the quantum state can acquire an arbitrary phase, not just the zero phase for bosons or the phase for fermions. And for some more complex states, these are non-abelian anyons. Exchanging them actually performs a non-trivial matrix operation, a unitary rotation, on a whole set of degenerate ground states. This property is incredibly powerful.
Non-abelian anyons and braiding statistics. I mean, it sounds like something from a quantum fantasy novel. But this isn't just exotic physics. You're saying this directly leads to one of the most promising blueprints for building a fault-tolerant quantum computer.
Exactly right. The biggest hurdle for practical quantum computing right now is decoherence, the incredibly fragile quantum information getting corrupted by noise from the environment. Topological quantum computing, or TQC, offers a potentially elegant solution. Instead of encoding qubits in single, easily perturbed particles like electrons or photons, TQC encodes them non-locally.
Non-locally. How?
It encodes them in the collective global topological state of multiple spatially separated non-abelian anyons. The information isn't held by just one particle, it's spread across their robust global relationships, how they're linked or braided. This non-local encoding provides inherent protection. A local perturbation, like a bit of thermal noise affecting just one or two anyons, simply cannot corrupt the encoded qubit because the information isn't there locally.
I see.
To cause an error, a disturbance would need to act coherently across macroscopic distances, affecting multiple anyons in just the right way, which is exponentially unlikely. This is fault tolerance by its very physical nature.
And the gates. How do you compute?
You perform quantum gates by physically braiding these anyons around each other in spacetime. You literally move them. The resulting unitary transformation, the gate operation, depends only on the topology of the braid, the overall pattern of the weave, not on the noisy exact path they took through space. So running an algorithm becomes like weaving a specific quantum braid. And the final measurement to get the answer is determined by a topological invariant of the link formed by the anyons' world lines, much like the Jones polynomial we talked about with Chern-Simons theory.
That's truly remarkable, a computer whose calculations are literally protected by the topology of how its components are woven together. Incredible. Okay, so from the incredibly tiny world of Indians, we can also scale up to the incomprehensibly vast. TQFT also serves as a crucial toy model and conceptual framework in the ongoing quest for quantum gravity.
Yeah, zooming way out now. A central challenge, maybe the central challenge of quantum gravity is that space-time itself is supposed to be dynamic. It's not a fixed background stage. TQFTs, being inherently metric independent, are therefore naturally background independent. This makes them ideal conceptual frameworks, sort of testing grounds for understanding what quantum space-time might be like. For instance, in loop quantum gravity, one approach to quantum gravity, the quantum states of spatial geometry are described by things called spin networks, and the quantum transitions between them are spin foams. These structures bear striking resemblances to the algebraic structures you find within TQFT.
Interesting connection there.
And even in string theory, TQFTs appear. There are things called topological string theories, which are basically twisted 2D sigma models used to compute complex mathematical invariants. TQFTs also show up as effective descriptions of certain simplified sectors within the larger, more complicated string theory framework.
So it's incredibly versatile, popping up everywhere from material science to the cosmos. But for all its power and elegance, it's crucial we understand what TQFT is not. It's clearly not a complete theory of fundamental physics as we currently know it. Why isn't the standard model, for example, a TQFT?
That's a critical distinction, absolutely. The physics we observe every day, the physics described by the standard model, particle interactions, energy, momentum, scattering, the whole causal structure of spacetime, all of this explicitly depends on the metric, on distances, angles, time intervals. A TQFT, with its metric-independent observables and often trivial Hamiltonian, simply lacks the necessary structure to describe these local propagating degrees of freedom, the dynamic dance of particles and forces that makes up our world.
So it's too simple in a way.
You could say that. It's too simple to capture the full, rich, dynamical content of our observable universe. TQFT excels at capturing these incredibly robust universal features like ground state degeneracy and condensed matter, these deep mathematical invariants, or the weird statistics of anyonians. It describes the solvable core, perhaps, or the foundational kinematic framework of quantum geometry. But it can't describe particle scattering and particle accelerators, the flow of time as we usually experience it, or massless propagating particles like photons or gravitons moving at the speed of light. It's fundamentally a theory of states and topological transitions, but not really of motion or energy propagation in the conventional sense.
Wow, okay. We've really got on a journey there. From the very abstract idea of physics independent of space-time geometry through its fascinating mathematical origins with people like Donaldson, Floer, Atiyah, Witten, we explored its two distinct constructions, Schwarz type and Witten type, saw its truly mind-blowing applications in condensed matter like the FQHE and anyons, potential for fault-tolerant quantum computing, and even hints towards quantum gravity. And finally, understood its inherent limitations. It doesn't do everything. So what does this all mean for us listening to this? TQFT really stands as this incredible intellectual bridge, doesn't it? Connecting fields that seem so far apart, offering profound physical intuition for abstract mathematics and rigorous mathematical language for new physics. It's a testament to that unreasonable effectiveness of both mathematics and physics in understanding our universe, revealing how concepts like gauge invariance and path integration are deeply, deeply intertwined with the very structure of space, time, and form itself.
Absolutely. And the ongoing legacy of TQFT isn't really about replacing theories like the standard model. It's about complementing them, continuing to illuminate these universal topological structures that seem to underpin reality at a very deep level, from classifying higher dimensional manifolds, which is still a huge challenge in math, to potentially designing the most robust quantum computers we can imagine. Its impact is enduring and, frankly, still unfolding. We're still finding new connections. So maybe as you reflect on this deep dive, consider this. What other fundamental, unchanging truths might be hidden away within all the fluctuations of geometry and dynamics that we see, just waiting perhaps for a topological lens to bring them into focus?